Finally, we can see what the physical meaning of the real value characteristic impedance really is. It's simple. The infinite lossless line we saw earlier has a structure that looks like this. Inductor L and capacitor C are both buckets. So when our signal comes in from the left, its energy is passed from the inductor to the capacitor, and then from the capacitor to the next inductor, one after the other, endlessly. So the signal gets propagated on the line. What does it mean to say one after the other endlessly? It means that there is something in the distance that continues to take energy away from the source, as if a resistor is connected to the other end of the transmission line. Because a resistor is something that can continuously consume the energy provided by source, this leads to the meaning of the real value characteristic impedance, and that is, the wave is propagating. If we find out the characteristic impedance is a complex number, it has a real part and an imaginary part, and the real part represents the propagation, and the imaginary part represents the unpropagation. Why does the imaginary part represent the inability to propagate? Because it is like someone stealing some of the energy during the wave propagation and not allowing it to travel to the far side. Furthermore, when considering the lossy line, we will see that the loss factors of R and G in the transmission line model are playing a role in the characteristic impedance. In conclusion, the characteristic impedance is the ratio of the voltage wave to the current wave, and it expresses the characteristic of whether or not the line is capable of propagating energy.